Hello, Algebra 1. So today we're looking at lesson 1.6, solving compound inequalities and special cases. Less emphasis on the special cases, but we will talk about them. So compound inequalities are pretty interesting. Lots of applications in the world that we live in, and you're going to see some examples of those in your homework and also in the notes here today. So let's dive in. What's going to happen is you're going to have an inequality that's joined by two inequalities that are joined by and or. You're going to have those words in the problem. So let's examine that with our first example. It says a number x is greater than -8. And one technique is just to go ahead and translate it directly. X is greater than -8. And now we're still talking about x. X is less than or equal to 4. Now, you've written the compound inequality. That's all great, but it's customary in the math world to combine and inequalities into a single inequality statement. So here's how you do that. Put the smaller number on the left, the bigger number on the right, x in the middle. And then you're going to describe each inequality with this single x. X is less than or equal to 4, and x is, be careful here, greater than, because you're reading it from right to left, x is greater than -8. This is the preferred way to write and compound inequalities. So, and one reason it's nice to write it this way is that commonly in application problems, you would read this as the number, the temperature, or whatever it is, the temperature is between -8 and 4. It's kind of a quick way to describe this. And also you can see x is in the middle, it's between them. So yeah, it's just a nice way to express it. Now to graph these, I'm not especially picky. Put the smaller number on the left, the bigger number on the right. You do need to get the circles versus dots accurate. There's going to be a dot at the 4 because it can be 4. It's going to be a circle at the -8 because it can't be -8. But double check here. X is less than or equal to 4. Greater than 8. Do you guys see how they're going to overlap? So I want you to shade in the middle. Even if you're used to just using arrows, I want you to shade in the middle. All right, so for part B, we've got a number y is at most 0. So I'm going to translate that directly. Is at most. Oh, okay, so if it's at most 0, it's going to be less than or equal to 0. Or, still talking about y, at least 2. And if it's at least 2, it's going to be greater than or equal to 2. It's at least 2. And with an or compound inequality, you leave it separate, which is kind of nice. And then to graph it, still want to do smaller number to the left, bigger number to the right, get your circles versus dots accurate. And if it's an or problem, it should shade on the outside, but we do want to check because it could be a special case. Basically, these special cases are either going to be all real numbers or it's going to be no solution because kind of they got the relationship wrong, they described it wrong. But in this case, y is greater than or equal to 2, y is less than or equal to 0, so I like to shade on the outside. So or problems you shade on the outside and problems you shade on the inside, as long as they're described correctly, and you do want to check that. All right, so for example 2, we're going to move on to solving them. And to solve them, you're usually going to be asked to solve and graph them because the graph can communicate some meaning there. So to solve compound and inequalities, you basically got to realize that you're solving two inequalities. You're solving x minus 2 is less than 3, but you're also solving x minus 2 is greater than negative 4. Now, you don't have to write it out as two problems. You can go ahead and say, well, if I'm adding 2 here, I'm going to have to add 2 to solve this inequality, but I'm also going to have to add 2 to solve that inequality to keep everything balanced. So we'll get a negative 2 is less than x is less than 5. Like so. And because we've got x by itself in the middle here, we are done. We solved it. And we can graph it. And less than 5, greater than 2, it works out to be a classic AND problem. On this next one, two-step equation. Subtract the 1 from everything. Divide the negative 2 to everything. And we're dividing by a negative to multiple sides of inequalities. So we got to flip the inequality symbols. Don't forget that. And then we're going to get a negative 4 here and a 2 here. And I would say we're done. But I do want to point out, customarily, they don't write the AND inequalities this way. Customarily, we always put the negative number first, and then you just got to translate everything appropriately. Greater than or equal to negative 4, less than 2. This is the preferred answer. Go ahead and flip that around. That's preferred. And then when you go to graph it, make sure you got the circles versus dots correct. Less than 2, greater than or equal to 4. It's going to be shaded in the middle. All right, let's flip it over here. By the way, if I'm going too fast, you can always pause the video and work them out on your own. Go at your own pace. Now, for OR compound inequalities, you're stuck basically just solving two separate problems, solving each inequality separately, which, could be worse, I guess, but yeah. So add the 5 to solve this. 3y is, whoops, isn't that funny how my mind wanted to add that equal sign? So got to watch that, don't you? Divide by 3, y is less than negative 1. Or we've got to solve the other side, plus 1. Or y is greater than 3. And then that's our answer. But then when we go to graph it, let's double check, make sure it's not some weird special case. So negative 1, 3, circles, greater than 3, less than negative 1. It is a classic OR problem, and it looks good. For the next one, same deal. You got to solve both inequalities here. Let's subtract the 7 over. That's going to get us 6. Divide by 2. Over here, add the 2 over. Divide by a negative 3. Oh, dividing by a negative on both sides. So greater than or equal to negative 4. And then let's graph this, see what it looks like. So we've got smaller number on the left, bigger number on the right, a circle at the 3, a dot at the negative 4. And then check this out. Y is greater than. It's going the wrong way for an OR problem. So something is up here. It's either they messed it up, it's not OR, it's an AND problem, or there's something else going on here. So let's take a look. So you're going to go this way, and then this one is this way. Now, that makes it look like an AND problem, but because it used the word ORs, you don't have to satisfy both of these. You're just satisfying one or the other. So what that means is you would keep going in both directions. And notice the entire number line is covered. I'm not scribbling that out because it's wrong. I'm shading the entire number line, which means in this case, it's going to be all real numbers. Now, I got to caution you, this is not very common. They don't mess things up this commonly. But anyway, on On the word problem down here, it's mostly just kind of understanding it. Electrical devices should operate effectively within a specified temperature range. Outside the operating temperature range, the device may fail. And I know with my phone, I often use it for navigation, going to a place I've never been before, so I bring up typically the Google Maps, but and as it's routing, it's up on the dash, and man, we've had some hot days this summer, and my phone will shut down and it'll say, you know, warning, the phone's not going to work until it cools off. And so this is a legit concern. All right, so it says, write a compound inequality that represents the possible operating temperatures of the smartphone if the operating temperature is 0 degrees Celsius to 35 degrees Celsius. So that's the ideal temperature. The operating temperature is between 0 degrees Celsius and 35 degrees Celsius. If it's between those, this is an and problem. And I'm going to translate it directly because we've got 0, 35, and our temperature. So to be 35 is okay is the way they describe it. So it needs to be less than or equal to 35 degrees Celsius and greater than or equal to 0 degrees Celsius. That is our inequality there. And then it says to describe one situation in which the surrounding temperature could be below the operating range. Well, if it's below the operating range, it's got to be below 0. So -1 would be below. That would be trouble. And then a temperature which would be above, so above the normal, the ideal possible operating temperatures, 36. 36 and above would be an issue. -1 degrees and below would be an issue. All right, thanks for watching. Have a great day.